Exponential decay. Now, here's what's going on with exponential decay. The only difference here, when we had your exponential growth graphs, if A was positive, it did that. If A was negative, it did that. Yeah. It's coming around. Graph paper's coming around.
Oh, they just checked. Oh, no. Fine.
Trader, would you mind grabbing some more graph paper? It's right there by your other stuff there. All right.
Never mind. Greta's the only one.
It's because she was too busy on her phone. Anyway, so the only difference between exponential decay problems and the exponential growth problems, instead of the graphs looking like this, the graphs will look like that. They just go the other direction. Or, well, that didn't work. Anyway. So, here's what happens when you have exponential decay. You still have the same function, f of x is a times b to the x, but here's the differences. A is greater than 0, and b is larger than 0, but smaller than 1. That's the only difference between telling whether it's a growth or a decay problem. The b values become a fraction. That's it. The a value is still positive. If the a value is negative, it just means that the direction of the graph is going to flip around. Thank you very much. I appreciate that so much. The difference is you still graph that parent function, and then you still graph the shift. So nothing really changes here. It really doesn't get too screwy. The only thing you just got to realize is that there might be a time on a test I might just ask you, is this a growth or a decay problem? That's it. And that means you have to know if b is not a fraction, it's larger than 1, it's growth. If it's decay, it's between 0 and 1. Okay? So let's look at some problems. Same idea. In this case here, you have your value of a is 1. Your value of b is 1/2. So when you go to graph this, you're still going to use your graphing calculator. Since there's no shift involved here, there's no h or k, this is basically your parent function right away. So as you go to the graphing calculator, what was it, 1/2? In this case, I'm just going to do 0.5 to the x. Graph. You'll see how it's just going the other direction. Okay? The graphs are just going the other direction from what they were last time. We still go to our table function. Let's scroll back up. It's like scientific notation. It's really, you can see how it's getting to become a really, really small number. So once again, I start out with my graph. Yeah, I bring my table around. At -3, it was 8. At -2, it's 4. -1 is 2. 0 is 1. 1 is 1/2, and so on. Okay? You still wind up with the same rules when you have the your asymptotes. Remember the horizontal asymptote that we had earlier? It was always at y equaled what? K, yeah. What is the k value in this case here? 0. All right. So you will see that when we go to graph exponential growth or exponential decay, they follow the exact same rules, exact same patterns. It's just have to know which one you have. And if you guys have a calculator in front of you anyway, you should never get that question wrong because you can just look at the graphs. Well, hopefully. So like I said, we remember this, right? So it's the same rules. We'll have the exact same rules. So let's take a look at this. I have y equals -3 times the quantity 1/2 to the x plus 2, all plus 1. When I hear Maddie's already saying it, a value, b value, your h value, and your k value. A is -3, b is 1/2, What's your h value?
-2.
-2, very good. And your k value? 1. So you go to graph your parent function at y equals -3 times 1/2 to the x. We graph that one first to get your generic points, and then you're going to shift everything left 2 and up 1. Equals -3 times so it's coming from the up. Go to your table. Your y-intercept is still your value of a. Oh, not in this case, I'm sorry. Grab this backwards here. There you go. So we have I can't graph anything until I get to about -2. -2, it's at -12. -1, it's -6. At 0, it's -3. 1, it's at -1.5, and -3/4, and so on. So here is your parent function. Your asymptote is at your value of k. So now we have an asymptote at k. So we put that in. And for each of these points, we go left 2, up 1. Left 2, up 1, so we're at 11. Left 2, up 1. Left 2, up 1. Left 2, up 1. Left 2, up 1. And so on. Oops. And there you go. So if you did okay with the exponential growth graphs, which sounds like most of you guys did, you followed the exact same rule. The h and k's don't change. The rules are all still the same. You plot your parent function, and then you shift it. Okay. Want to see one more before we get into word problems? Go ahead and do that one. We go back and we just go back to your table, get your parent function. Your parent function here was -4 times 1/4 to the x. So 0, it's -4. At -1 was way off the chart. 1 is -1. And 2 is -1/4. So each of these points, we have to do what to it?
Move it to the left. Move it right.
Left or right?
Left.
H is, remember, opposite sign. So move it to the left 0, or 1. All right. I just moved the graph. I was just being nerdy. All right, let's try some word problems. That's usually where people start to get a little crazy. So instead of having a growth factor now, we're going to have what's called a decay factor. Now, once again, your percentages, you always convert your percentages to decimals. So in this case here, you have your initial amount, which is your A value. Your R is your rate as a percentage, and T is generally time. It's usually years in this case. So let's say you have an initial amount of $500. Your rate is 8%. When I write out the actual equation with those two parts, you wind up with y equals 500 times 1 minus 0.08 to the t. Now what the book will do in this case is that they will automatically simplify 1 minus 0.08. You get 0.92. So you're going to see it written out like that. And this is kind of what you were asking earlier. When you see it as, when you just see 0.92, you should be able to tell what your percentage is. That means you have an 8%. Great. Okay, because what they're doing is they're subtracting things right away. All right? You guys are like children. Oh my God, it's Greta. It is Greta. I watched her. She's like freaking out. She has to wave to people. She keeps going like, there's so many people.
No, I don't know them. I just can't not do distraction.
That's why I got rid of distraction.
But I like to be distracted.
No, you? Yes, I can. I just can't have a shot.
Yeah,
Alright, so just a little. Alright, so that's what you're going to see in this case here. Now, once again, this 1 minus r, that 0.92, would be considered the decay factor. You see decay a lot of times with what's called depreciation. If any of you guys have ever bought a car, the moment you drive it off the lot, it's worth a lot less than what you bought it for. Usually speaking, there are some cars that depreciate faster than others. Let's see. Ones that hold the resale value the best, you'll figure this out once you guys all get ready to save your money for cars, are usually going to be, you know, like your Toyotas and Hondas and stuff like that. Those generally hold their values really, really well. No, they do. I mean, seriously. You look at a lot of them. I mean, even like my Suburban, brand new Suburban like mine, $62,000. Okay. A year later, it's 40 grand. So you don't buy a brand new thing like that because then someone else take that depreciation principle hit, and you take. That's why used car values are where they are. Okay. So here's what happens. So if you buy a new car for 24 grand, what's your initial amount? 24 grand. That is, put it away. Thought you were reading. I apologize. So your initial amount is 24 grand. Your rate is 16%. So that's 0.16. When it says write the exponential decay model to estimate the car value after 2 years. So your T is going to be 2. So what you wind up with is 24,000 times 1 minus 0.16 squared. Now, the next part, it says graph the model. Really? You want to graph something that has a line intercept of 24 grand? No, not really. So here's what I would have you do. Of course, because what I would have you do is use the graph to estimate when this thing is worth what? You go to the table. Okay? So what I would do is that we know that instead of, guys, please, instead of, once you get this is what the model is for after 2 years, when you have to estimate when the car is going to be worth 12 grand, you change that to your variable. Okay? That 2 becomes your variable, because that's what you're trying to solve for. So in my graphing calculator, I would type in the 24,000 times 0.84 to the x. And I would look in my table function of y values to look for when it's about 12 grand. And that'll figure out how many years it took to depreciate that much. Yeah. You know, if it's between the two, I would just say go between 13 and 14 years. You know, and stuff like that. Because it's not going to give you a dead, I mean, sometimes it might give you a straight answer, but yeah, if you guys, like you say, it happens between 13 and 14 years. So your answer would be somewhere between 13 and 14 years. What's that? 24.
You're not between 3 and 4.
Oh, did you say 3 and 4? Did you say 13? I thought you said 13 and 14. That's why you guys are freaking out. Sorry about that. It was between 3 and 4 years. I'm sorry. Yeah, between 3 and 4 years, it drops below that value. So really, as you get into the word problems with these things, they're very, very similar to what we did earlier. Really not a lot of tricks. Go ahead and try this one. Try and write out the equation for this. You have a stereo system for $780. Stereo system. My wife and I were planning some camping trips this summer, and we're camping up in Michigan. And the campground, when I'm registering through the state of whatever their DNR, it asked for my home phone, business phone, cell phone, and pager number. Hello, 1996. I thought it was pretty funny. Huh? I don't have a pager. A pager was, it was really cool back in the early 90s, you know, for drug dealers and doctors. You would get, a pager was just basically caller ID. That's all it was. So let's say someone wanted you to call them, they would call your pager and just type in their phone number, and you would have to know whose phone number that was. It wouldn't say, oh, it's Rachel. You know, it would say, no. All it would just be, it'd go beep, 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 and you would look at it, and it would just list out a phone number. That's all it would do. Yes. Hey, did someone page me? That's what it was. But nobody had phones. This is 94, like 92, 93. All right, it's not 96. Like 92, 91, somewhere in that area. People didn't have cell phones. Really, believe me, people didn't have cell phones when they were in high school at some point, not too long ago. People had to carry quarters. You guys know what a quarter looks like? It's round and metal, and it's worth 25 cents. There's this other thing called a payphone. You ever heard of those? Have you ever used one?
Yes.
I don't know.
Anyway, now I digress. 780. Hopefully we got this right. Don't worry about the whole pager thing. It's not the end of the world. It's seriously. Let's say you're a doctor and they had to get a hold of you and you didn't have a cell phone because cell phones were just too expensive back then. You had a pager and your doctor's office has a special phone number. So if you see that phone number, I gotta get to my doctor. I gotta call to see what's wrong. Betty Smith has a heart attack. We have to go in and save her. Okay, it was seriously, that's the reason why they had pagers, was to be able to get a hold of somebody to have them contact them. All right? And that's a lot of times where the alphanumeric texting started, because people were typing in letters that would spell out, or numbers that would spell out words using the alphanumeric text. That's where text messaging started. So you learn a little bit something new every day. Did you guys get this for your answer?
Yes.
Yeah.